Assalamualaikum and good day to panels. So my name is Hartine Binti Mohammad Ganesan and my final year project is entitled Introduction of Barium Titanate as an Interfacial Layer between Titanium Dioxide, Electron Transport Layer and Tin-based Perovskite Absorber in Perovskite Solar Cells using SCAPS 1D. So, perovskite solar cells are among the most promising photovoltaic technologies due to their high efficiency and low manufacturing costs. However, charge recombination occurring at the interface between the electron transport layer and the absorber layer can significantly reduce device performance. Therefore, this project proposes the introduction of barium titanate, or we can say as BaTiO3, as an interfacial layer to improve the charge transport and reduce the recombination losses. So this entire study is carried out by using SCAPS 1D simulation software. Let's move to project description. So, perovskite solar cells have attracted significant attention because of their potential to achieve high efficiency at a lower production cost compared to conventional silicon solar cells. So, in this project, a tin-based perovskite absorber was selected because it is considered a lead-free alternative and it is more environmentally friendly. However, losses due to their carrier recombination still limit the device performance. So, to overcome this issue, a barium titanate interfacial layer was introduced between the titanium dioxide electron transport layer and the tin-based perovskite absorber layer. So, this layer is expected to facilitate charge extraction and improve overall solar cell efficiency. So, let's move on to the objective of this project. So, the objectives of these projects are firstly to simulate and evaluate the performance of perovskite solar cells with a barium titanate interfacial layer by using SCAPS 1D. And secondly is to investigate the effect of barium titanate thickness on key photovoltaic parameters, including open circuit voltage, short circuit current density, fill factor, and power conversion efficiency. So, the third objective is to determine the optimum barium titanate thickness that could provide the best solar cell performance, which we could say the best power conversion efficiency. So, now let's look the device structure. We can see that this figure shows that the comparison between the baseline and the proposed solar cell structures. So the baseline structure consists of fluorine doped tin oxide front contact (FTO), titanium dioxide electron transport layer (TiO2), tin-based perovskite absorber layer (CH3 NH3 SNI3), copper iodide hole transport layer (CUI), and platinum back contact (PT). So in this proposed structure, a barium titanate interfacial layer is inserted between the titanium dioxide layer and the tin-based perovskite absorber layer. So the purpose of this modification is to improve the carrier transport while reducing the recombination losses. Okay, now let's see, why do we choose barium titanate? Barium titanate was selected because of its excellent electrical properties. So it possesses high dielectric constant, good charge transport capability, and good interface compatibility with perovskite materials. So these properties will help improve carrier separation and reduce the recombination at the interface. So as a result, barium titanate has strong potential as an interfacial layer for enhancing the solar cell performance. Now let's move to the methodology part. So the project began with a literature review and collection of material parameters from published journals. So next, the baseline solar cell structure was developed by using SCAPS 1D simulation software. After we validate the baseline model, a barium titanate interfacial layer was introduced between the titanium dioxide layer and the tin-based perovskite absorber layer. And for the barium titanate, the thickness we varied from 1 nanometer to 100 nanometer. And for each of the thickness value, the photovoltaic parameters that we extracted is open circuit voltage (VOC), short circuit current density (JSC), fill factor (FF), and power conversion efficiency (PCE). So these results we analyzed to determine the optimum thickness. So now let's look to the result part. Let's see the thickness optimization that I have done. So this graph shows the effect of barium titanate thickness on power conversion efficiency. So as we can see here, the highest efficiency was achieved at a thickness of 1 nanometer with a power conversion efficiency of 29.58%. So as the thickness increased, the efficiency gradually decreased. This indicates that an ultra-thin barium titanate layer provides the most effective pathway for charge transport. So when the layer becomes thicker, additional resistance may be introduced, which reduce the device performance. Therefore, the optimum barium titanate thickness obtained in this study is 1 nanometer. So let's see for the performance comparison. So as we can see, this graph compares the baseline solar cell and the optimized solar cell with a 1 nanometer barium titanate interfacial layer. So for the baseline device, the open circuit voltage was 1.117 volts, short circuit current density was 29.50 milliampere per square centimeter, and fill factor was 86.01%, power conversion efficiency was 28.35%. So this is before we introduce barium titanate. So now, if after we introduce the barium titanate layer, we can see the open circuit voltage become 1.111 volts, short circuit current density increased to 32.24 milliampere per square centimeter, fill factor is 82.53%, and the power conversion efficiency increased to 29.58%. So the efficiency improved by approximately 4.34% compared to the baseline device. Although the open circuit voltage and fill factor decreased slightly, the significant increase in short circuit current density resulted in a higher overall efficiency. So I can say that this suggests that the barium titanate layer successfully improved charge collection within the device. Moving on to the novelty and innovation. So the novelty of this project lies in the introduction of a barium titanate interfacial layer into a lead-free tin-based perovskite solar cells. In addition, systematic thickness optimization was performed by using SCAPS 1D simulation, and the finding demonstrate that even a very thin barium titanate layer can significantly improve device performance. So for the sustainability and SDG, Sustainability Development Goal 7, Affordable and Clean Energy, and Sustainable Development Goal 9, Industry Innovation and Infrastructure. By improving solar cell efficiency, this work contributes to the development of cleaner and more sustainable energy technologies. So the use of simulation also reduces material waste and development costs before the fabrication happens. So the potential application, the proposed solar cell structure has potential applications in high efficiency solar panels, building integrated photovoltaic systems, portable renewable energy device, and future lead-free photovoltaic technologies. So the simulation approach also enables cost-effective optimization before actual device fabrication. In conclusion, a barium titanate interfacial layer was successfully introduced between the titanium dioxide lateral transport layer and the tin-based perovskite absorber layer using SCAPS 1D simulation. So the optimum barium titanate thickness was determined to be 1 nanometer, and at this thickness, the device achieved a maximum power conversion efficiency of 29.58%, which is higher than the baseline efficiency of 28.35%. So the results indicates that barium titanate effectively improved charge transport and enhanced the overall performance of the solar cell. Therefore, barium titanate is a promising interfacial material for future high-efficiency lead-free perovskite solar cells. So that's all from me. Thank you for your attention.